right. Looking or thinking back to the previous lesson when you were solving using the box method, was anyone able to find a more efficient or quicker way to factor the previous trinomials? And these are some examples of trinomials similar to what you would have solved in the previous assignment. Compare the expanded polynomial to the factors. And do you notice anything about the numbers? Look at the 6 and the 2 and see how they relate to the 8 and the 12. Look at the 4 and the 2 and see how they relate to the 6 and the 8. Do you see a pattern? Well, if you think back to the box method yesterday, remember we were finding factors of 12, and then when we did our diagonal multiplication, they needed to add up to 8. So let's have a look here. Do 6 and 2 multiply to 12? The answer is yes. Do 6 plus 2 add up to 8? The answer is yes. Let's see if that pattern holds true on the next one. Multiplying to 8. 4 and 2 multiply to 8. 4 and 2 add to 6. Let's check this one down here. Negative 4 times negative 3 is positive 12. Negative 4 plus a negative 3 is negative 7. Look at this last one here. Negative 11 times negative 3 is positive 33. Negative 11 plus negative 3, negative 14. So a more efficient or quicker way would be, let's say we have this one, u squared minus 12u plus 27. You are looking for two numbers that multiply to 27 and add to negative 12. Because we are dealing with u's, we are going to start each of our factors with a u, and we have 9 and 3 multiply to 27. If they are both negative, they will add to negative 12. So that is a shorter method. Now, one of the things I want you to notice, if you look at all of the squared terms in these, what was the coefficient on all of these squared terms? The answer is 1. This method, this shortcut, only works if your squared terms have a coefficient of 1. If they do not, we cannot use this shortcut. But we know if you don't understand the shortcut, or if you forget the shortcut, the box method will work. Let's do some more of the box method. Here, if we look, these squared terms do not have a coefficient of 1. So we cannot use that effective method that we just learned. We actually need to use the box method. Now again, if you think about your factors of 4, you've got 1 and 4 or 2 and 2. And remember we said most times, not all the time, but most times the two that are closest together will work. So we'll try 2 and 2. Of 9, we've got 1 and 9 or 3 and 3. So we're going to try 3 and 3. Multiply across the diagonal. That is not going to work. We are not going to get 20. Sometimes you might just change the order in one of your columns. But in this case, that's not going to work because they were the same number. So we need to simply try a different combination of factors. Now, sometimes you're going to get it right off the bat, and other times it's going to take you a little bit longer to figure out which two you need. That's where the trial and error comes into play. So I'm going to leave the 2 and the 2, but I'm going to change the factors of 9 to 9 and 1. 2 times 9 is 18. 2 times 1 is 2. They do add up to 20. I'm dealing with h's. Both of these stay positive. So my factors are 2h plus 9 and 2h plus 1. And again, we could multiply this out and see if we get the original polynomial to make sure we have done it correctly. Let's try another one. Possible factors of 6 would be 2 and 3, or 6 and 1. So I'm going to try the 2 and the 3. Possible factors of 35 are 5 and 7. Now, because they're different numbers, we may not write them in the right order the first time. Just pick a combination and go from there and see if it will work. We get 15 and 14. That is not going to give us negative 11. Instead of trying a different set of factors, let's switch our order and see if it will make a difference. 3 times 7 is 21. 2 times 5 is 10. We need negative 11. That will work, making the 21 negative. Because the 21 is negative, you go on the diagonal that you multiplied, and you make the second number a negative. The 5 stays positive, and we are dealing with k's. Now, it's very important that we remember our factors are coming from within the box. So 2k minus 7, 3k plus 5. I see a lot of students use the 2 and the k and then the 21. That is not what we want. Our factors are the numbers that are in the box. Let's try another one. It's just a matter of keeping and practicing and seeing how all of this will work. Now, if we use 4 and we go by our rules to pick the two that are closest together, we'd have 2 and 2, and the 6 we'd have 2 and 3. But I can tell you right off the bat that this is not going to work. And it's not because I've done the diagonal multiplication in my head. It's because I have a 2 and a 2 in the same row. Having the same number or multiples of a number in the same row would tell me that there would be a greatest common factor that could come out. But if you look at the question, 4, 11, and 6, they do not have a common factor. So that will not work. Changing the order here doesn't work either because the first column was both 2's. So we need to try a different option. Maybe I'll make these 4 and 1, and then I'm going to use 3 and 2. Now, my order is going to be very specific. I cannot put 2 in the same row as the 4 because, again, that would indicate there was a common factor. 1 times 3 is 3. 4 times 2 is 8. Can we get to 11? The answer is yes. 3 plus 8 is 11. Both of these are positives. We are dealing with g's. 4g plus 3, that comes from within the box, and g plus 2. Again, the second row of the box. All right, looking at this next one. Again, we'll start with 2 and 3. And factors of 10 are 2 and 5, but I'm not going to place the 2's in the same row. They can be on the same diagonal, but they cannot be in the same row. Will 15 and 4 get me 7? The answer is no. Swapping these around won't work because it'll put 2 and 2 on the same row. So we need to change one of the set of factors. So maybe I try 6 and 1, and then I use 5 and 2. Again, I could not put the 6 and 2 in the same row because they would have a common factor. So we have 5 and 12. Can I get to negative 7? The answer is yes. If I make the 12 negative, 5 subtract 12 is negative 7. So therefore the 2 becomes negative, the 5 stays positive, and we're dealing with m's. 6m plus 5, m minus 2. All right, a little bit different. This is just understanding what it is that we're doing. Evaluate 3x squared minus 14x plus 15 when x equals 2. So we're going to replace the x's with 2, and we're going to evaluate the expression. 2 squared is 4. 14 times 2 is 28. So we have 12 minus 28, plus 15. 12 minus 28 is negative 16. Plus 15, we get negative 1. So we evaluate, we get negative 1. Now we are asked to factor that polynomial. Possible factors of 3 are 3 and 1. Of 15 are 5 and 3. We have 5 and 9. Does that give us negative 14? The answer would be yes if they were both negative. So we have 3x minus 5 and x minus 3. Now, if we evaluated 3x minus 5 and x minus 3 when x equals 2, what do you think the answer should be? Hopefully you say negative 1. We've used the same polynomial. We're just writing the polynomial in a different way. We're writing it as a product of factors. So we should still end up with the same value. 2 times 3 is 6. 6 subtract 5 is 1. 1 times negative 1 is negative 1. So the answer is still the same. So that just shows you that whether it's in factored form or expanded form, it is the same polynomial. You get the same result.